Hi folks, today we're going to talk about correlation versus causation and try and understand the differences between these two topics. So without further ado, let's get started with our search for causation in our minds here. And what most people do is they set up a study where they have a response variable which measures an outcome of a study, and they have also an explanatory or an independent variable which influences change in that response variable. So basically, people set up studies trying to look for cause and effect relationships. Now, to keep in mind when graphing these things, we'll actually graph these things in a scatter plot coming up here soon enough. The variable x will always be your explanatory variable, which is, you might know more as independent variable, and that y variable is actually your dependent, or what we'll call here is a response variable. So let's look at some examples and see if we can determine the difference between explanatory and response variables. So let's say we have two exercise physiologists completing an experiment on the effect of smoking on an individual's VO2 max. That's basically our body's capacity of transporting oxygen. So if the physiologist took a sample of runners while recording their number of cigarettes used per week and their VO2 max, what would actually be our explanatory and response variables? Well, reading through this, what are they trying to look? Well, the effect smoking has on an individual's VO2 max. So when you take a look at it, your explanatory, also known as your independent variable, that has to be the smoking. While the response or dependent variable, it depends upon something, would have to be your VO2 max, because we're looking, smoking causes a VO2 max of a certain type. So our explanatory is the number of cigarettes used per week, and the VO2 max is our response variable. Now, let's take a look at another study. So let's say we have a recent poll of people from Savannah, and observers record an individual's income level and years of income. What are the explanatory and response variables in this observation? So we're looking for kind of a cause and effect type of situation. If you take a look closely, you might say, oh, well, years of education influences income level. However, others might argue that if you have a given income level, you'll be able to go and get more education. So in this case, with this study set up as is, there are no explanatory or response variables. But people couldn't put a twist on their study if they're trying to learn about impact from one on the other. So let's take a look at this as an example. Economists wish to find the impact education has on a person's income level for people living in the Savannah area, and the economists conduct each experiment by asking each individual the number of years of education and that person's current income level. Now we do have explanatory and response variables. If you notice, we're looking for the impact education has on a person's income level. So in terms of our explanatory or independent variable, that's the education that we're looking to cause the influence on the person's income level. So the explanatory variable will be the education, years of education there, and the response variable will actually be the person's income level. So now that we've seen these explanatory and response variables, in terms of our studies, people are trying to look for this cause and effect relationship. So what does that mean? Well, they're looking for causation. And what causation refers to is an event resulting in the occurrence of another event. So basically, if you have variables or events x and y, you're looking for an event x to cause or trigger basically a response in event y. So most people, what they're doing, are searching for methods for proving causation. That's the key. Most people are looking to prove causation. However, the downside is they look in the wrong places to do this. So there's things to support evidence of causation, but it is going to be much easier to show that there's no causation between variables. So that's what we're going to look at from here on out, and what people usually use for these methods and the differences between those. So moving into what a scatter plot is, a scatter plot basically demonstrates the relationship between two quantitative variables measured on the same individual. And then in those scatter plots, we're going to have the x-axis being marked by one variable and the y-axis being marking the other. And each point on the graph is referring to one individual and just two variables for that one individual. And as we mentioned before, you'll have explanatory variables and response variables occur from time to time. You want to put that explanatory variable on the x-axis. That means your response variable is necessarily on the y. So without further ado, let's take a look back at one of our earlier examples. We had that physiologist experiment on smoking's effect on an individual's VO2 max. Let's say we have the following table for 11 runners, okay? And we want to look at this data and actually list the points. Well, your explanatory variable, that was the number of cigarettes used per week, which was 20. And the response variable was that VO2 max, which is 60. So with that in mind, what actually happens here? Well, if we're to list our first point, we had that 20 for our x value and 60 for the y value for that first individual. Notice it doesn't pair different numbers like 20 and 32 or 20 and 55 because we're lining up per individual. So for example, the next one, the x value, number of cigarettes used, would be 45. That means the y value for that individual would be 32 in terms of milliliters of oxygen per kilogram of body weight per minute there. And then our next point, we'd end up with 355. And our point after that would be 068. And then I think you get the idea. We can keep on going down the list, making all these ordered pairs that we see in our table. Now the key with a scatter plot, though, remember this refers to an x and y axis, so we're actually going to graph this thing. And so graphing that information, if you have all those pieces there, you have the points 20, 60, 45, 32, another ordered pair 355. If we plot these on that Cartesian plane, all of a sudden we get something that looks like this, the scatter plot with all these dots listed here. So if you look for 2060, all you need to do is look at the graph and you see this value right here. That's 2060. 4532, we can locate that one as well. That's right at this point. And so on and so forth. We can go on down the list. Just remember that your x-axis will always be referring to the cigarettes, and your y-axis will be that max VO2. So moving a little further, if we actually wanted to separate, toss in a third category, we can do that as well. There's actually multiple ways to do this. Let's say the bold in the regular text here represent different categories of male and female. So if we wanted to mix and match our dots, we could do it like so. Put an M for male, an F for female, and now we have a third variable existing on our data set. So it doesn't just stop with two, but mostly we will focus on just the two variables in terms of our quantitative variables for these studies. But obviously there's going to be more than just two for most of the studies that go on. So moving forward, okay, if we have another type of scatter plot, let's go back to our income level and years of education. Notice with that experiment how the economist set it up in that second one. We had a first version that didn't quite work out for explanatory and response, but the second one that did, we can have education on that x-axis and income in thousands on the y-axis, and then let's say this is our graph. We can actually draw information from scatter plots, and so that's what we'll talk about. So in the first case, what is the range of incomes of individuals in this experiment? So income levels, notice we need to look at the y-axis, and what we're going to do is we're going to kind of draw this Mendoza line that goes at the bottom and at the top of these. So if you look at the bottom, we have a line that would probably occur right about here, maybe. And with that line, if we go to the corresponding y value, once again we're looking at the y-axis here, what range would that be? Approximately, we'll say maybe 17, 18,000, somewhere in that range. And then we could do the same for the top end. If you look at the top end, we draw a line across. We can kind of ballpark it 97, 98,000. So incomes range from about 17, 18,000 to 97, 98,000, somewhere in that vicinity. Okay, so we actually have an idea of what income ranges we can expect. Moving forward, we can do another problem. What's the longest time an individual has spent in the educational system? That's not too hard. All we need to look at now is the x-axis. So we're going to take our lines and move them up and down. And it's pretty easy to see Actually on the shortest end as well, so 0 years, which seems like it doesn't make sense, but that does happen from time to time. People don't spend any time in the educational system. Um, but if you look at the far right-hand side, looking at the X values, we have someone that's been in the educational system for 25 years, and that one's not too bad to look up. So we have all that information at our disposal. So it seems like scatter plots are a good thing. But, so for example, what percent of the sample has an income of more than 60,000? This might seem like a reasonable question. We could count all the dots, but what we don't know for sure is, do some of the dots lie on top of one another? So we could have multiple points for a dot that we just see as one. We could have 4, 5, 6 dots for that individual value. So when looking at this, we will not have a good answer. And so that's some of the drawbacks in terms of scatter plots. Okay, so keep that in mind. There's certain things that scatter plots can do. There's certain things that they can't do. However, what we try and do is we try and display information and get a good feel as to what's going on once we see the scatter plot. So is there a relationship between years of education and a person's income level? Can we answer that? Well, maybe not right now, but we're going to get a nice answer for this in just a second, and that's what we're trying to look at, and this leads into correlation. So in order to talk about correlation, though, we're going to need a few steps in that process. The first step is positive and negative association. So this talks about the direction of a scatter plot. So two variables are said to have positive association if high values of the two variables tend to occur together. So if you have an increase in, say, an x variable, that means an increase in the y variable as well. With negative association, though, high values of one variable tend to occur with low values of the other. So if your x value is increasing, that means your y value would technically be decreasing if you're looking at the scatter plot. This direction of scatter plots, that gives us some information that we'll tend to use a little bit later. Okay, so when taking a look at the scatter plots, we also need to talk about form, and basically that's we have different sorts of relationships like linear relationships, exponential relationships, quadratic relationships, but the main focus here is going to be linear relationships, and we're going to talk about how close things resemble a line. So is our scatter plot close to a straight line pattern? Keeping that in mind, if you take a look at this, okay, we can actually talk about whether or not this is close to a straight line, whether or not it's a positive or negative association. So this is an example of a linear relationship, right? It's fairly close to what's going on. Now, in terms of the association, what's happening there, we have a positive association, and it's pretty close to a straight line. So what we say, this is a strong, actually this one's really strong, a really strong linear relationship and positive association. So you can kind of see that happening right there. And it was almost a perfect line, just with the exception of those two dots sitting at those points. So basically, when we're talking how strong is our scatter plot, we're talking about how closely it resembles a line. This strength notion will change if we're not talking about linear relationships too. But just keep in mind, for us, we're just keeping things simple, dealing with lines for right now. So when examining the scatter plots, what we're looking for is an overall pattern that involves the direction, form, and strength. Okay, so direction, form, strength are the main three components. So how closely, in terms of the form and strength, we're keeping those in terms of linear relationships here. And from there, we can kind of look for outliers and deviations from that pattern. So the linear correlation, and we'll just drop this and call it correlation, but in our case, since we're dealing with linear relationships between two quantitative variables, we're talking about linear correlation. So basically what we're looking for is, are there some form of a positive association or a negative association involved with this, along with that linear relationship. Okay, so if we have the scatter plot, can we plot it with 5, 3 being the first point, 11, 5 being the second point, 20, 13 being the third point, 41, 24 the fourth point, and 26, 12 the fifth point? Yes, of course we can. We can get them in this increasing order. 5, 3 occurs right here. 11, 5 occurs at this point, and so on and so forth. You can you can kind of get the idea as the x value increases. Notice our y value, for the most part, is increasing, with the exception to that 1.2612. Now, does this scatter plot have a linear correlation, right? Well, yeah, it can be closely approximated by a line. And so what we actually say has a positive association, and it's a strong linear correlation. So strongly correlated values based upon those numbers. Okay, so this leads us to our first fact. Notice in that example, I talked about correlation, but there was no mention about an explanatory or response variable. This is where most people get hung up. They think you always have to have an explanatory and response variable. The fact is, no. Okay, you do not have to have those two types of variables in order to talk about correlation. So, second fact, when you're talking about the direction of a scatter plot with strong linear correlation, the direction will always depend upon the slope. And what do we mean by that? The slope, if you're going from reading the graph from left to right, if the graph is going up as you go from left to right, it's going to be a positive slope. If it's going down as you go from left to right, that's going to be a negative slope. So if the slope of the line is positive, meaning going up as you read the graph from left to right, there's a positive association. If the slope of the line is negative, then there's a negative association between the two variables. So meaning negative slope, meaning once again as you read the graph from left to right, you see the graph falling down. So those are some facts about correlation that we're going to have in our back pocket to use here. So when you take a look at this graph, are the two variables in this scatter plot linearly correlated? And we want to determine, is it positive, negative, association, strong, weak, what's going on here? Well, if you look, there's no line, no matter how we try and draw this. I mean, you can look at a random assortment of lines. There's no quick fix that grabs all these. As a matter of fact, we can't tell a trend in terms of this graph whatsoever. So is there a positive association, negative association? We don't know. So this means no, there's really not any correlation between these points. And this can happen sometimes. And this can be useful because if you're looking for cause and effect relationships along the way, if the data values aren't even correlated, that means there is no cause and effect relationship. Okay? So if in order to have causation, you will need at least to show that there's some correlation. But we'll look here in just a bit. That doesn't necessarily mean vice versa. Okay? So now let's look at this example. If you take a look at this, look, we can kind of approximate this one by a nice line. Granted, not every point's going to be on there, but we can tell there's some sort of downtrend if we were to draw a line from left to right. And so this means there's negative association, and it's fairly strongly linearly correlated. So we have a strong linear correlation with negative association. Okay. Looking at this one, hopefully you can see that all these points, if we're trying to determine the correlation that we're dealing with, this is a perfect line, so you can't get any better than that. And it's positive association because high values of the one variable tend to occur with high values of the other. So we have a strong, actually it's perfect, linear correlation and with positive association. Okay. Now, let's go back to our VO2 max example. If we wanted to actually provide some statistical analysis, what could we say? Well, if you notice, as the number of cigarettes increase, you see this line sitting right there that's there to approximate. It's fairly strong in terms of its linear correlation. So, oh, and by the way, strong and weak, that might seem like a relative term. There's actually a way to define these later on. You can get a correlation coefficient. We just don't discuss that just yet. So statistics, you can get into linear correlation coefficients, have a better definition of those terms. So now taking a look at this, if you notice the downward trend in our line when we read it from left to right, that means negative slope. That means there's negative association. We have pretty closely resembling a straight line, so means we have a strong negative association. And so with that in mind, what we want to see is if we have that information, with the correlation being strong and negative association between those, can we actually say that smoking causes a person's VO2 max to decline? This is the big difference. I know a lot of you might be saying, well, yes, of course. Actually, from these studies, as they're set up, the answer is not as of yet, okay? And let me kind of explain. The key factor here is what we call lurking variables, and they exist inside of here. So, for example, if you're checking someone's VO2 max, things that can play a role is a person's age. If you're having someone that's 95 and determining their VO2 max, that might not be as high as someone in their early 20s. Same thing for body mass. If someone has a quite high body mass index value, it might be harder for them to get their VO2 max up there. So keeping those things in mind, we can't come out and say that even though there's a correlation, that there is a causation, because there's just too many variables for us to be concerned with. And this leads us to the moral of the story here. Okay? Correlation does not necessarily imply causation. Now, so you do have causation implies correlation, right? So if the event X causes the event Y to occur, you can say for a fact that X and Y must have a strong correlation. Okay? However, what most people tend to do is they think because there's correlation that that's going to imply causation. That's a big mistake that occurs over and over again in many statistical studies, and I want you all to prevent yourselves from doing this. So if you have two events are correlated, that does not, I repeat, it does not necessarily imply that one event causes the other. Keep that in mind when running statistical studies, as this is the important concept. Correlation does not imply causation.